Today, we are going to trace the journey of energy. We'll look at how we take it simply like a simple sugar cell or sugar like glucose and turn it into the universal currency of the cell, ATP. We will cover how we will build the components and finally how the machine known as ATP synthase actually manufactures that energy. So we are going over all 15 pages to your left on this presentation. My name is Reagan Smith, and let's get to it. So in this, we can see that this pathway acts as a sugar architect. It possesses glucose 6-phosphate to generate that ribose 5-phosphate, which is the essential structural sugar needed to build the backbone of our nucleotides. And we will see this appear more. We will see this ribose 5-phosphate appear more and more. We can also, just other than glucose, we can utilize alternative fuels. This shows, in this, we can see how lactose is broken down into galactose, which then uses a specialized transferase system to be converted into glucose 1,5-phosphate, so it can enter the central metabolic stream. So we're really trying to get to a glucose-centric area. In this, this image just outlines that lipid metabolism, specifically detailing the conversion of glycerol and fatty acids into energy-rich intermediates. It also demonstrates the process of ketogenesis, which you can see at the bottom, which produces ketone bodies like acetone when acetyl-CoA accumulates. This image, this is the de novo biosynthesis pathways for both pyrimidines and purine nucleotides. It highlights how precursors like PRPP and various amino acids are assembled through multi-step enzymatic reactions to generate fundamental building blocks such as uridyllate and inosinate. And then we can look here that uridyllate and inosinate the uridyllate can be converted into UTP, CTP, and TTP, as well as inosinate being converted into ATP and GTP, which are vital for DNA replication. I always want to say uridyllate as uridyllite, but I know that's not really how it's pronounced. Here we see the turbine engine of the cell. The C subunit rotates as protons, which will always be H+, flow through it, forcing the beta subunits to cycle through the open, loose, and tight states, which physically joins ADP and PI to manufacture ATP. You'll see the ADP goes into that loose subunit, and then it'll tighten around it, and by adding water, we see that it turns that ADP into ATP. So here we see our primary energy extraction pathway. This is breaking down glucose into pyruvate, generating ATP and the high energy electron carrier NADH, which acts as a shuttle to power our final energy production steps. Shout out to glycolysis. Now, if glycolysis is not happening, we may need some gluconeogenesis, in which we are synthesizing glucose kind of from scratch. So through this, we reverse that glycolysis using unique bypass enzymes like PEPCK. You can see at this bottom left, PEPCK is the enzyme that turns phosphoenol pyruvate into oxaloacetate, and then, that's the oxaloacetate, turning into the phosphoenol pyruvate using the PEPCK to convert non-carbohydrates sources like lactate or glycerol back into usable glucose. So here, this is just documenting that lipid biosynthesis, illustrating how glycerol 3 phosphate is utilized to form phosphatidate and eventually triaglycerols. It also maps the mevalonate pathway, showing the step-by-step conversion of HMG CoA into 3-isopentenyl pyrophosphate, and that's more on the bottom, and also that dimethylyl pyrophosphate. Pardon me. So here, I apologize for its lightness. This image just highlights that amino acid metabolism, including the role of glutamate in the urea cycle and the synthesis of ornithine. Additionally, it shows the pathway for synthesizing like serine and glycine from 3-phosphoglycerate, as well as the conversion of phenylalanine to tyrosine. So here we can look at one of our major, probably the biggest generator of ATP. So complexes 1 through 4 use these electrons from NADH and FADH2 to pump protons across the membrane, creating that electrochemical gradient that provides the power for our ATP synthase engine. This is the metabolic hub here. Here the pyruvate dehydrogenase complex feeds acetyl-CoA into the citric acid cycle, where we strip away those electrons to load onto NADH and FADH2, which are the fuels for our electron transport chain. Here we just see this illustrates metabolic integration through aminotransferase enzymes. We swap groups, turning alanine into pyruvate, aspartate, into oxaloacetate, or creating glutamate, just allowing amino acids to feed directly into the citric acid cycle. Now we're almost finished. This is the tail end of building complex lipids. We follow the conversion of isopentenyl pyrophosphates into squalene, and finally the cyclization steps. The creation of the cholesterol molecule. So here, we're managing like sulfur-containing amino acids. It was just tracking the transformation of methionine into SAM, which is just S-adenyl acid. Acenyl. It's a long word. You can look at the picture, or you can look at it. Just SAM. And that just cycles through homocysteine, and then showing how we balance those amino acid pools and produce essential molecules like cysteine and succinyl-CoA. Anyway, thank you for listening. My name is Macy Smith, and I am signing off this final poster presentation for Biochem 1.